But you have a separation of charge, a higher density of negative charge on one end versus on the other end. And so this is called an induced dipole. Okay, a neutral molecule or atom becomes a dipole in the presence of an applied electric field. You had a short homework problem that was due today that just quantified this a little bit more. We talked last time about the dipole, or when we were dealing with dipoles, we talked about this quantity called dipole moment, electric dipole moment, which is given the symbol P. It's Q times S, where Q is the magnitude of the charge on either end. Okay, so in this case, it's negative E, or E, little e, for example. And S is the separation, the amount of distance that the two ends are separated. So that dipole moment here, the strength of the dipole in ordinary matter or usual insulators can be parameterized with this quantity called alpha. This is the atomic polarizability. It's just telling you the extent to which a neutral atom becomes a dipole when there's an electric field applied to it. So you can think of this as the applied electric field due to some other external charge acting at the presence of some atom, and it creates a dipole moment. It causes it to polarize. And it's a property of the material. It's a property of matter. Okay, so for example, carbon atoms, a carbon atom has a particular atomic polarizability of something like 10 to the minus 40, and the units are coulomb meters over newtons per coulomb. It's just, again, it's just a parameter or a property of the material, and the larger the atomic polarizability, the more it's going to polarize, the bigger the dipole moment's going to be when you apply the same electric field. This is a pretty tiny number, but when you have lots and lots and lots of atoms in a material, then it adds up. Okay, so you get to see large effects. We can see the tape being attracted to my hand, even though the individual molecules may be polarizing only a tiny, tiny bit. Okay, so you had a brief question on that.